All right, welcome everyone. Today we're going to dive into a real cornerstone of quantitative business analysis. Now we're going to talk about a concept that, look, it might seem purely mathematical at first glance, but I promise you it's the silent engine driving countless financial models, growth projections, and strategic decisions in the business world. We're talking about the natural exponential function, often written as e to the power of x. And this isn't just another formula to memorize. Think of it as the fundamental language for describing how value, markets, and even ideas grow, organically and continuously. For those of you pursuing a degree in business administration, a deep, intuitive understanding of this function isn't just helpful, it's absolutely non-negotiable for a successful career. So let's start with a big question, one that really challenges our basic assumptions about how we measure things. I want you to think about the value of a stock on the market. Does its price update once a day, or maybe once an hour? No way. In our hyper-connected, high-frequency trading world, that value is in constant flux. It's shifting with every single transaction, every piece of news, every millisecond. Or think about a new technology catching on. It doesn't spread in these neat, predictable jumps, right? It diffuses through a population continuously. The very same thing applies to an investment that's compounding interest, not annually, not quarterly, but in a constant, unbroken stream. So the central problem for any serious financial analyst is this: how do we build a mathematical model that actually captures this reality of unending, seamless growth? That is the intellectual challenge we are here to tackle today. So here's our game plan for the session. We're going to start by really getting a solid understanding of continuous growth, and we'll see how it's different from the simpler, discrete models you've probably seen before. Then we'll introduce the star of our show, the function e to the x, and we'll explore the unique mathematical property that makes it just so perfect for this job. After that, we'll roll up our sleeves and apply all this theory to a practical financial modeling problem, the kind of thing you'll actually face in your careers. And finally, and this part is crucial, I'm going to walk you through the common mistakes and conceptual traps that students often fall into so you can apply this powerful tool with both accuracy and confidence. Let's get into our first section. This might be the most important conceptual leap you'll make in this course. In your intro finance or accounting classes, you probably worked with simple periodic calculations, right? Interest paid at the end of the year, revenue booked at the end of the quarter. And those are fine. They're useful approximations. But the real world of high finance, of market dynamics, and corporate growth is so much more fluid than that. Our goal here is to shift our thinking from these distinct, separate steps to really understanding and modeling a constant, uninterrupted flow of change. This slide really gives us a great visual for what we're talking about. Over on the left, you see discrete growth, and it's pictured perfectly as a staircase. Imagine you put money into a simple savings account that pays interest once a year. On December 31st, bam, your balance jumps up to the next step. But for that whole year before, the value was static. It's simple, sure, but it's also a pretty artificial way to look at growth. Now, look to the right. Continuous growth is that smooth, upward-sloping ramp. There are no sudden jumps. At every single moment, every second, every nanosecond, a tiny bit of value is being added. This is a much more accurate model for things like the fluctuating value of a corporate bond portfolio or the compounding effect you see in really sophisticated investment vehicles. One is like taking a snapshot, the other is like watching a live video stream. Okay, so now that we see why we need a model that can handle this smooth, ramp-like growth, we have to ask ourselves, what mathematical tool can actually describe a process like that? Your standard linear or polynomial functions, they just won't cut it. We need something special. We need a function whose very nature embodies this principle of self-reinforcing growth. And that perfect function, as we're about to see, is the natural exponential function, e to the power of x. So what exactly is this function? Well, the definition right here on the slide is the absolute key. It describes a system where the rate of growth is directly proportional to its current value. Let's really break that down. Proportional just means there's a constant, direct relationship. If the value doubles, the rate of growth also doubles. The classic snowball analogy is perfect here. As a snowball rolls downhill, it gets bigger. And that larger size, its greater surface area, allows it to pick up snow even faster. The growth literally feeds itself. In business terms, think of a company with a strong brand reputation. The stronger its reputation, that's the current value. The faster it can attract new customers, that's the rate of growth. Well, e to the x is the purest mathematical expression of this self-reinforcing dynamic. This brings us to the most remarkable, honestly, almost magical property of this function. It's a property that makes it the absolute cornerstone of growth modeling. Now, to understand it, we need to briefly touch on a concept from calculus, the derivative. Don't let the term intimidate you. For our purposes, as business analysts, you can just think of the derivative as a precise measure of the instantaneous rate of change. It's like looking at the speedometer of a car at one specific moment to see exactly how fast it's going. The incredible property of e to the x is this. Its derivative, its instantaneous rate of change, is just e to the x itself. It is the only non-zero function in all of mathematics that is its own derivative. And this isn't just some mathematical curiosity, folks. It's the very reason it's the perfect model for continuous growth, as we're about to see. So let's translate that mathematical rule into plain English. This quote really nails it. If we want to know how fast our function is growing at any given moment, if we want to check its speedometer, we don't need to do some complicated new calculation. We just need to look at its current value, its current position. For the function e to the x, the value and the rate of growth are completely locked together. They are one and the same. This slide shows the idea perfectly in a financial context. Let's imagine your investment portfolio, which is compounding continuously, has just hit a value of exactly $100,000. Because its growth is perfectly modeled by this natural exponential function, at that precise instant, its value is increasing at a rate of $100,000 per unit of time, let's say per year. Now, when that portfolio grows to $500,000, guess what? Its growth rate will have accelerated to $500,000 per year. The larger the asset base, the faster it generates new wealth. This one-to-one relationship between size and speed is the crucial takeaway here. All right, so we've laid the theoretical groundwork. But the true test of any quantitative tool in business isn't how elegant it is, it's how useful it is. So now we're going to move into the application phase of our lecture. Let's see how we can actually use this powerful concept to analyze a common financial scenario and make a data-driven recommendation. This is where your understanding goes from academic to professional. Here's your scenario. Imagine you're a junior financial analyst at an investment firm. A client gives you $10,000 to invest for 5 years. You found a low-risk asset that offers a nominal interest rate of 5% per year. Now, your firm offers 2 products based on this asset. One that compounds interest annually, and a more sophisticated one that compounds continuously. Your job is to figure out which option gives a higher return, and then present a clear mathematical justification for your recommendation to the client. This is a classic foundational problem in finance. Okay, to solve the continuous compounding part of this, we use this really elegant and powerful formula. It says the final amount, A, is equal to the initial principal, P, multiplied by E, raised to the power of the interest rate, R, times time t. Let's walk through this step by step, just like you should on an exam or in a report. Step 1, identify our variables. Our principal P is that initial investment, $10,000. Our time T is the investment horizon, 5 years. Our rate, R, is 5%. But, and this is a really critical point we'll come back to, we have to express this as a decimal. So R is 0.05. Step 2 and 3, calculate the exponent. That's just R times T. So we multiply 0.05 by 5, which gives us 0.25. Think of that number as the total growth factor over the whole period. Step 4, solve for E. Now we grab our calculators and find the value of E raised to the power of 0.25. That should give us about 1.284. This is the total multiplier effect of that continuous growth. And finally, step 5, calculate the final amount. We just multiply our initial principal of $10,000 by that multiplier 1.284, and that will give us our final answer. And here are the results of our calculations, laid out nice and clear. So after 5 years, the standard annual compounding option gets you $12,762.82. The continuous compounding option, using the formula we just walked through, gets you $12,840.25. Now, at first glance, you might be tempted to say, the difference is only about $77, that's minor. But as a business professional, you have to always think in terms of scale. On a $10,000 investment, sure, it's $77, but on a $1 million corporate bond investment, that same percentage difference is nearly $8,000 of extra return. And for a corporate treasurer managing a $1 billion cash reserve, that seemingly tiny difference becomes an extra $8 million in earnings. The key principle to remember is this. For any given nominal interest rate, continuous compounding represents the theoretical maximum possible return, and the function e to the x is the mathematical key that unlocks it. So, we've seen the power and the application of this function, but, in any quantitative field, knowing the right formulas is really only half the battle. Knowing where people usually trip up, knowing the common pitfalls, that's just as important for making sure your work is accurate and professional. So in this final section, we're going to go over the most common mistakes students make so that you can consciously avoid them in your own work. Please pay close attention here. These are the 4 big ones. First, and this is a fundamental error,
Don't confuse an exponential function like e to the x with a power function like x squared. They might look a little similar, but they behave in completely different ways, especially in calculus. The rules for their derivatives are not interchangeable. Second, be super careful with your calculator. Before any exam, seriously, take the time to find the e to the x button. It might be labeled e to the x or XPR, and practice using it. One simple keystroke error can totally torpedo your results. Third, and this is probably the mistake I see most often, always convert your percentage rate to its decimal equivalent before you plug it into the formula. A 5% rate must be entered as 0.05. If you forget and just punch in the number 5, your answer will be astronomically, ridiculously wrong. Finally, there's the conceptual mix-up. Use the right model for the right situation. The continuous model is incredibly powerful, but if you're analyzing a bond that specifically says it pays interest only twice a year, well, then a discrete semi-annual model is the right choice. You have to match your tool to the reality of the financial instrument.
So as we wrap up our lecture, what's the single most important thing I want you to walk away with? It's this. The function e to the x is so much more than just some abstract math concept. It is the fundamental language we use to describe, to model, and to predict any system that shows continuous, self-reinforcing growth. From the appreciation of financial assets to the viral spread of a marketing campaign, this elegant function is the engine running under the hood of modern quantitative analysis. And I'll leave you with one final thought, a question to carry with you into your next strategy or management class. We've just established, mathematically, that for any system modeled by e to the x, its rate of growth is a direct function of its current size. Now, what does that imply for how you should think about running a business? It suggests that every dollar of profit you reinvest, every new loyal customer you get, doesn't just add to your company's size in a linear way. It fundamentally increases your capacity for future growth. The path to massive scale isn't just about adding more resources. It's about building a system that compounds them. I want you to think about that connection between mathematics and strategy. Thank you.